In this video, we're going to start a new chapter with the solubility and complex ion equilibria, although we're actually only going to focus on solubility. So we're talking about the solubility of insoluble salts. So as you know, silver chloride is insoluble. But in reality, when we say that, yes, there's a large amount of silver chloride in the bottom of this beaker, some of the ions still make it up into solution. And so it's an equilibria in which silver chloride as a solid goes to form silver plus chloride minus. And so this concentration, so that we're going to be able to calculate the concentration of this in the equilibria. The way we're going to do this is the solubility product constant. This is an equilibrium constant for slightly soluble or nearly insoluble ionic compounds. When we write out the solubility product constant expression, there's no reactants because they're solids. It is temperature dependent, but we're not going to worry about the temperature dependent. So the equation from the previous page was the silver chloride as a solid goes to form silver ions plus chloride minus in an equilibrium. So the KSP for this expression simply becomes the Ag plus concentration times the chloride concentration. So it is important to remember that this is in molarity. So let's do an example. First of all, so first asked to write out the solubility product constants for the following expressions. So first thing is to write out the equation. So I have BaSO4. And as always, it's important to recognize the fact that SO4 is an ion. It doesn't break up. It doesn't break up into S and 4 oxygens. So this goes to form Ba 2 plus SO4 2 minus. The charges are not that important. But then the KSP is still going to be the products of the reactants, but the products are not included because they're solids. So it's going to be concentration of barium times concentration of sulfate. And that's all I need to do there. Okay? So I suggest pausing and then coming back to get the answer for the next one. Okay, for the next one, when I put iron 3 hydroxide into water, okay, it's going to form iron 3 plus and 3 OH minuses. Again, OH is a polyatomic ion. So this time the KSP is going to be the concentration of iron times the concentration of hydroxide, but this time it's raised to the third. And the last one, again, pause the video and work it out and see if you get the right answer. I have calcium phosphate. Goes to form 3 calciums plus 2 PO4, 3 minuses. And so the KSP expression is going to be the concentration of calcium cubed and the concentration of phosphate squared. Okay, so important part is to realize that the subscripts become the coefficients and then they become the powers here. Okay, so the subscripts here become the coefficients there, which become the powers there. But polyatomic ions, so this is sulfate here, polyatomic ion stays as 1. So even though there's 4 here, that stays as SO4, and so the coefficient there is 1 and the coefficient there is 1. When there's more than one of them, there'll be a parentheses, and then the coefficient, the subscript here becomes that coefficient, which becomes that power. Okay. So now we want to calculate the solubility product constant from solubility data. So it wants to know what is the KSP of silver chloride if the solubility is 1.9 times 10 to the minus third grams per liter. Okay. So we want to know what KSP is. Okay. And the solubility of AgCl is 1.9 times 10 to the minus 3. This is in grams per liter. So the expression is going to be AgCl goes to form Ag plus Cl minus. Okay. Solubility is at equilibrium. So for these, I don't need the ice table. I'm just going to have E. Of course, there's no silver chloride because of the fact that that's a solid. Okay. However, the KSP for this is bracket of silver, bracket of chloride, and the brackets mean molarity, which is moles per liter. I have grams per liter, so I need the molar mass to go between grams and moles. So the molar mass of silver chloride is 143.32. I have 1.9 times 10 to the minus 3 grams per liter. So that means I want grams to cancel. It needs to go on the bottom. So 143.32 grams on the bottom, moles on top. And so I get a solubility and molarity of 1.326 times 10 to the minus 5th molar. So now I'm just going to plug it into this expression, the KSP. So that means that this is going to be 1.326 times 10 to the minus 5th. And this is going to be 1.326 times 10 to the minus 5th. So my KSP is going to be 1.326 times 10 to the minus 5th times 1.326 times 10 to the minus 5th. And I get 1.76 times 10 to the minus 10th. And as with most, I'm not going to worry about it, but if there was a unit there, it'd be molarity squared because I have molarity times molarity. Okay, I'm not going to worry about the molarity units. Okay, I'm going to stop this video here, and we will do more examples on the next slide.